Welcome to Study Loop.
So in this problem, we have to find out or calculate the solubility of CuX in an NaCN solution of 0.15 molar, and we are given the Ksp value or the solubility product constant for CuX. So what we have to do here, we have to first find out the equilibrium constant for the dissolution of CuX in NaCN, and from the equilibrium constant value expression we'll be able to find out the solubility of CuX. So CuX will be dissolved in NaCN in two steps. In first step, it will be dissociated in its ions. So CuX is in solid form, and then it will be dissolved or will be dissociated to form Cu2 plus in aqueous and X2 minus in aqueous. And the Ksp value or the solubility product constant value we are given is basically the constant for this reaction. So the Ksp value will go along as 1.27 times 10 to the power minus 36. And then this Cu2 plus will react with the cyanide ion from NaCN to form Cu CN4 2 minus. And since we have 4 cyanide here, we have to put a 4 here, and we have to know the formation constant for the formation of this, and the formation constant or Kf value for this is 1 times 10 to the power 20 25, yeah. And then if we just sum up these two equation here, we can cut copper here, and the overall net equation will be CuCN4 2 minus and aqueous plus X2 minus, and the equilibrium constant for this um, reaction of CuX with NaCN, or the solubility of CuX in NaCN. The equilibrium constant here is basically the multiplication of these two constant. So equilibrium constant will be Ksp times Kf, and the value we'll get is 1.27 times 10 to the power minus 11. So this is the equilibrium constant for the dissolution of CuX in Cn minus. Now we'll have to set up an ice table for this dissolution reaction. For that, let's just write the equation one more time. So we are reacting copper sulfate of copper X in solid form plus 4Cn minus. So we are just rewriting the net reaction equation, and then we will have CuCN4 2 minus plus X2 minus. And now we have to form an ice table for this. So since CuX is a solid, and as we don't include solid and liquids in the equilibrium constant expression, we can ignore this. So what was our initial concentration for cyanide? So the initial concentration of cyanide is basically the concentration of the NaCN, because uh, 1 molar NaCN will produce 1 molar cyanide ion. That means if the concentration of NaCN is 0.15 molar, that means this is the concentration of Cn minus also. If we go back here, so initial concentration of Cn minus is 0.15 molar, and then our initial concentration of CuCN for 2 minus was 0. At the beginning we don't have anything formed yet, and also the X2 minus concentration is 0. And then if we consider the change in the concentration as S, or the molar solubility, then the change in Cn minus n will be 4S, since we have a 4 here. So the change for Cn minus will be, we will lose 4S, as we are considering S as the change in concentration, and then we have 1S added to both the products. So in the equilibrium, the concentrations will be 0.15 minus 4S, and for these two products it will be S and S. Now if we set up the equilibrium constant expression for this reaction, it will be K is equal to the product concentrations over the reactant concentration. It will be CuCN4 2 minus and X2 minus over the Cn minus, and we have 4 here, as we have a 4 cyanide ions. And then if we just put the values here, we will get our K value we calculated as 1.27 times 10 to the power minus 11 will be equal to, so in both of these are S and S, that means we will have S square on the top, and we will have 0.150 minus 4S whole to the power 4. And since S, we can consider S is very small compared to this 0.15 molar, we can ignore this value here and can rewrite this equation as S square over 0.150 whole to the power 4. And by just solving the equation, we can find the value of S, or the solubility, which will be 8.01 times 10 to the power minus 8. So this is the solubility of CuX in 0.15 molar NaCN.